Okay, welcome to another simple engineering snippet. In this video, we'll be working through an example where we apply conservation of momentum to a control volume. Hope you find it useful. Okay, so we have a fire hose nozzle that we need to determine how many firefighters are going to be necessary to hold this nozzle in place. And an average firefighter can apply 300 pounds force or an SI, 1335 newtons. And we will be working this problem in both English engineering and SI units. All right, so Reynolds transport theorem is the tool that we are going to be applying to conservation momentum to get the following relationship. So this is the conservation momentum applied to a control volume. This is F is equal to ma. And this is a vector equation, so it's always good to define our coordinates. And so we're going to take plus x as to the right, and the flow is going into the nozzle from left to right. And get the dimensions of the nozzles in both inches and centimeters. And we want to simplify this equation. It's a vector equation, so we're going to turn it into, break it down into the x direction only. But the first thing we can do is recognize we will be doing a steady state analysis and set the partial derivative with respect to time term, the unsteady term, to 0. Okay, so let's just take this equation and recast it into the x direction. And to do that, just go ahead and note our velocity vector, where little u is our x component of velocity. And we do that, the integral form of conservation momentum in the x direction is the sum of the external forces in the x direction is equal to the integral of the control surface of the x component of velocity times the density times the dot product of the velocity with the unit normal outward vector. And that integral is done over the entire control surface. Okay, so we need to define our control volume. And we are going to select the control volume as being the actual nozzle plus the water inside the nozzle. Now this is important. We need to do that because we need to identify all the external forces, and if we had just taken the metal nozzle, then the water flowing through it would be an external force. That's going to be a complication that we're going to have to try to come through. So if we select both of them, then we don't have to worry about that because that's an internal force. All right, well, next let's add labels. So the inflow part of the nozzle is going to be port 1, and the outflow is port 2. And let's go ahead and define our flow. So we have the pressure at 1. The pressure at 2 is atmospheric. And we've provided the flow rate. Okay, so let's work on the left-hand side of this equation, the external forces in the x direction. And normally we would consider body forces, but gravity is going to be in the y direction. So there are going to be no body forces that we have to worry about in the x direction. Next, let's go to surface forces. And well, let's draw in the restraining force, Fr, and we've drawn it going in the positive x direction. So that's an assumption. If we get a positive answer, that means we selected correctly. If it's negative, then it's going in the minus x direction. All right, well, continuing on with surface forces, we need to worry about pressure forces. And so there's a pressure at 1, and that's going to be pressing in the positive x direction. It's always against the control volume, so that's going to be P1 times A1. We have a pressure at 2, and it's going to be pressing against the control volume in the minus x direction. So that's minus P2A2. But then again, the pressure at 2 is atmospheric, and there's pressure at atmospheric all around this control volume. So we're going to use gauge pressure to determine our external pressure forces. So pressure at 2 is going to be 0. All right, so that's good for the left-hand side. Now let's work on our surface integral. And we have to integrate this wherever flow is passing a boundary. And we have two sections, port 1 and port 2. So let's work on each one of those. So starting with the integral at port 1, well, we have the x component of velocity times the density times the dot product of velocity at 1 dotted with the unit normal outward vector. And so we're going to need the actual velocity, so that's just the volumetric flow rate divided by the area. So we'll be able to do that. And we'll note that the x component of velocity at 1 is just going to be equal to the magnitude of V1, and it is in the positive x direction. Now let's look at our unit normal at 1, and it's going to be always pointing away from the control volume, so it's going to be in the minus x direction. And more importantly, with the velocity at 1, it makes an angle of 180 degrees, and so that dot product is going to return a negative sign. So we're going to have a positive and a negative. So a positive and a negative, is the product is going to be a negative, and so our inlet flow term is going to be minus rho v1 squared times a1. All right, now let's do the same thing for 2. And well, u2 again is the exponent velocity at 2 is again going to be in the positive x direction. And n2 is outward from the control surface, so it's also in the positive x direction. So the angle between the velocity and the unit normal outward vector is 0 degrees, so that's going to return a positive sign, as so. And so we have a positive times a positive, so we get a positive. All right, so now we have one equation, one unknown. Let's start working on the terms and get numerical values, starting with the pressure force at 1. And so P1 times A1, here's our equation for both English engineering and SI. Both of them units work out pretty well. And we get these answers. Now let's work about the inflow term. And so write down all of our values. And well, for the SI, as we expect, the units work out kind of very nicely, and we're able to get an answer, but we're hoping to find pounds force in the English engineering equation, and that's not as straightforward. What do? Well, we're going to need our friend G sub C, and this is 1 over G sub C, to get the units of the desired units of pounds force. All right, well, let's do the same thing for the outflow term. And again, using our friend 1 over G sub C, and we can get readily solve for the answers. Okay, so now we have one equation, one unknown. We have all the values on the right-hand side, and we can get the answers. And we should note that we did return a negative sign, and that means that the assumed direction for the restraining force, FR, was in the wrong direction. It's actually in the minus X direction. So the firefighters are actually pulling on the nozzle to keep it in place because Mother Nature wants to send it out in the other direction. That's really probably not what we were expecting. So let's investigate that a little bit. If we look at the pressure drop through the nozzle, it can be calculated with an equation of this form where we have a minor loss or a form loss, I denoted as K nozzle, times the dynamic pressure, and typically use the highest pressure for your device or your fitting, and that's going to be the velocity at 2. Well, we don't know what the nozzle minor loss coefficient is, but we know everything else, so we can calculate that, and we would expect it to be somewhere between I don't know, maybe 0.25 for a really well-designed nozzle, and I expect it to be less than 1. And why am I doing this is because, well, it was a pressure term at 1 that was overwhelming the problem, and maybe we have too high of a pressure at 1. It's unrealistic. So if our form loss for our nozzle is really high, that would show that, this is an academic problem, and they specified the pressure being too high at the inflow. All right, so putting in our values and solving for it, well, we get a nozzle minor loss coefficient or form factor of 0.36. Man, that's pretty reasonable. So although this came out as an academic problem, in reality, it's not. So the forces are indeed in the minus X direction for the given data. That's looks pretty realistic, but that's not what we were looking for. We were looking for the number of firefighters. So we get to take the force that each firefighter, an average firefighter, can apply and divide that into the required force. And, well, we get 2.8. And, well, we'll just take that up to 3. All right, well, I hope you found this problem useful. If you do, please like and subscribe, and have a great day.